Imagine setting off on a cross-country road trip, your car packed and your playlist queued up, only to realize halfway through that you'll need a truckload of fuel just to make it to your next stop. This scenario, frustratingly impractical for a road trip, parallels the predicament faced by traditional chemical rockets, incredibly powerful, yet voraciously fuel-hungry and limited in operational longevity. Now, the tides of technology are turning toward what might be likened to the Tesla of space travel, thrusters such as ion and electric propulsion systems, which signify a paradigm shift in how we approach journeying through the cosmos. Ion engines, in particular, are not the new kids on the block, theoretically. The idea was first conceptualized back in the 1910s by Konstantin Tsiolkovsky, a pioneer of astronautic theory. However, it's only been in the more recent decades that they shifted from scribbles on a page to powering real-life missions through space. Ion thrusters specialize in using a small amount of propellant at extremely high exhaust velocities. Imagine throwing a baseball as hard as you can. You expend a burst of energy similar to that of chemical rockets. Now, imagine instead that you have a machine that continuously throws tiny pebbles, but at speeds that would shatter sound barriers. That's the essence of an ion thruster, achieving speeds of about 90 kilometers per second. One might wonder about the efficiency of such a system. Traditional chemical rockets, despite their brute force, hover around 35% efficiency, meaning much of the energy they produce is lost. In comparison, ion thrusters can achieve up to a staggering 90% fuel efficiency. This stark difference stems from how the two systems use their fuel. While chemical rockets burn through their supply to create short, powerful bursts of speed, like our initial car analogy, ion engines use their fuel more judiciously, allowing for longer missions, like having an electric car with an ultra-efficient battery. Lest we believe this is all theoretical, the NASA Dawn mission stands as a testament to the capabilities of ion propulsion. The mission's craft orbited Vesta and Ceres, two of the largest bodies in the asteroid belt, for over 8 years, a feat that would have been exorbitantly impractical with chemical propulsion due to the sheer volume of required fuel. The Dawn spacecraft's longevity and maneuverability in deep space were made possible entirely by its trio of ion thrusters. Switching gears, or perhaps more aptly, switching currents, electric thrusters bring another flavor to the table. With variants such as the gridded ion and Hall effect thrusters, these systems swap out the mechanical exhaust of ions seen in chemical rockets for an elegant dance of electric and magnetic fields which accelerate the ions. The Hall effect thruster, in particular, has seen widespread adoption in satellites, including those of the Starlink constellation. These thrusters use less propellant and derive their energy from electrical sources, usually solar panels, heralding a new era of efficiency and sustainability in satellite technology. A particularly interesting point of debate is the choice of propellant. Xenon, argon, and krypton each carry their pros and cons, with argon emerging somewhat recently as a cost-effective alternative. SpaceX's decision to use argon for the Starlink satellites highlights the subtle, ongoing optimization and the balancing act between cost, availability, and performance in the realm of advanced propulsion technologies. However, these advancements do not come without their challenges. Material erosion stands out as a key issue, as the high-energy particles necessary for ionization and thrust can degrade the very systems designed to harness them. The development of more resilient materials and innovative engineering solutions is thus a critical frontier for the longevity and reliability of these thrusters. The future prospects for electric propulsion are not merely incremental improvements, but could represent leaps in our capability to explore deeper into space. The thrust-to-power ratio, operational time flexibility, and enhanced fuel efficiency lay the groundwork for missions that were previously confined to the realms of science fiction, missions to the outer planets, asteroids, and beyond. The journey from chemical rockets to advanced propulsion systems like ion and electric thrusters exemplifies the evolution from brute force approaches to to a more elegant mastery of physics and engineering in space exploration. As we stand on the precipice of expanding into our solar system, these technologies will not only propel our spacecraft, but also our ambitions further into the unknown, promising an exciting new chapter in the saga of human space exploration. And just like the mighty sailors of the starry ocean that is space, our quest for discovery continues, ever driven by the endless possibilities that lie in our universe.